Good evening, everybody. Okay, let us start. So today we will do the final part, that is the base theorem, and after and tomorrow let us do with the transcriptomics, and then tomorrow I will also discuss regarding the projects. One moment.
ఏదన్నా అటెండ్ గా
Okay, let us start. Sorry, there was I lost my internet connection. Okay, so my screen is visible to all. My voice is audible.
Yes, sir.
Yes, sir.
Okay, so Thomas Bayes, based on his theorem, we are today studying this Bayes theorem. So it is an advanced version of probability. So why are these slides? This is just to tell that whatever is going to be taught here is all probabilistic. So basically, inference is a method of statistical inference in which Bayes theorem is used to update the probability for an hypothesis as more evidence or information becomes available. Okay, so that is what it is showed here. In the first slide, you have just little information, and you have much more information given here. Silence. Okay. Bayesian inference is an important technique in statistics, especially in the mathematical statistics. Actually, it is used. Though we are hardly studying this particular thing in our statistics, but you can check it out because it is an advanced version of probability. Okay. Frequency, that is the probabilistic view of probability, is so called frequentistic approach, where the probability P of an uncertain event, that is A, which is denoted, if it is event, it is PA, is defined by the frequency of that event based on previous observation. It is that probability we are calculating based on the previous observation, what we have seen. So that also is going to happen. Example, in UK, 50.9% of all the babies born are girls. Suppose that we are interested in an event A randomly selected baby is a girl based on the past observation that 50.9% of the babies born are girls, like that, based on the past or the previous observations. According to the frequentistic approach, so probability of A will become 0.509. Okay. The frequentistic approach for defining the probability of an uncertain event is fine, providing that we have been able to record accurate information. This is important term here. Accurate information about many past incidents of the event. So we need to accurately record all the past instance for the same event. Then only we can predict the current event. However, if no such historical databases exist, then we have to consider a different approach. Bayesian probability is the formalism that allows us to reason about the beliefs under conditions of uncertainty. Example, like if you have observed that a particular event has happened, such that Britain coming 10th in the medal table at 2004 Olympics, then there is no uncertainty about it. So if in the past it has happened, immediate past, then we can be sure that okay, this time also it can be happening. However, suppose A is the statement where Britain sweeps the boards at 2012 London Olympics, winning 36 medals. Some examples are given here, you can see. Since this is a statement about the future event, nobody can state any certainty whether or not it is true. Different people may have different beliefs in the statement depending on their specific knowledge of factors that might affect its likelihood. So you have some example here. Henry may have a strong belief in the statement A based on his knowledge of the current team and past achievements. Marshall, on the other hand, may have a much weaker belief in the statement based on some inside knowledge about the status of British sports. Example, he might know British sportsmen failed in the bids to qualify for Euro 2008 in soccer. win the Rugby World Cup, and win the Formula One World Championship all in one weekend. So these are some of the past incidents. So the again one more is there. Thus, in general, a person's subjective belief in a statement A will depend on somebody of the knowledge K. Hence, we write this as the PAK. A being the event, sorry, A being the statement and K the event. Henry's belief in A is different from Marshall because they are using different Ks. That is the different beliefs or statements. However, even if they are using the same key, same K, they might still have different beliefs in A. The expression PA/K thus represents the belief measure. Sometimes for simplicity, when K remains constant, we just write PA, but you must be aware that this is a simplification. Okay, so coming to the theorem, true Bayesians actually consider conditional probability as much basic than joint probabilities. It is easy to define probability A bar B without reference to the joint probability, that is P A comma B. To see this notice, we can rearrange the conditional probability formula to get this one. I think everybody knows P A by B. PB is P A comma B. By symmetry, you have B by A. PA is A comma B again. So this is the final, that is the Bayes rule. Probability A by B is probability of B by A, PA divided by PB. So this particular rule, please remember it for the Bayesian theorem. The problems, whatever will be given, you have to remember this theorem, just this formula, so that you can be interpret your results. Okay. So, fundamental difference in the experimental approach: normally reject or fail to reject hypothesis 0, that is H0, based on an arbitrary chosen p-value. Conventionally, as we know, it is less than 0.05. In other words, we choose our willingness to accept a type 1 error. This tells about nothing about the probability of H1, which is non-null. That is alternate hypothesis. The frequency conclusion is restricted to the data at hand. It doesn't take into account the previous valuable information. Okay, in general, we want to relate an event E to a hypothesis H, and the probability of E given H, the probability of H being true is determined here. A probability distribution of the parameter or hypothesis is obtained, and you can compare the probabilities of different H for a same E. Conclusions depends on previous evidence. Bayesian approach is not data analysis per se. It brings different types of evidence to answer the questions of importance. Given a prior state of knowledge or belief, it tells how to update beliefs based upon observation, that is the current data. So these two last statements, you should remember it for analyzing the Bayes problems. So these are all actually probabilistic, that is observations. So Diana Plato died of a drug overdose at the age of 34. That is just, we can say, observation. Todd Bridge, on suspension of shooting and stabbing, alleged the drug dealer in a crack house. So these are all, whatever you can see in the picture, are based just on the observations. Even this is also based on more of hypothesis. Our hypothesis is young actors have more probability of becoming drug addicts. So you have taken the matrix like YA plus being the D plus being the drug addicted and D negative without drug, and you can see how they have done it. Young actors with control, that is A minus. actors YA and drug addicted, it means like 3 have come here, and non-drug addicted is 7, that is total 10. So addicted and non-addicted. This is for the control. So control, you have just 1 drug addicted and 29 are non-drug addicted of the 40 samples. With a frequentistic approach, we test conditions A and B have different effects. Young actors have different probability of becoming drug addicts than the rest of the people. So in the null hypothesis, there is no difference in the effect of the conditions of A and B. The statistical choice is x square y8 in the correction. So here we cannot reject the null hypothesis. That is the final conclusion based on this probability that we are not able to reject the null hypothesis. Is given us is basically, if we do 7% of the times we will obtain this result if there is no difference between both the conditions. And we have strong belief that young actors have more probability of becoming drug addicts. So you can just ignore these calculations. We're just coming to the final conclusion what we have seen in the last. Okay, some of the examples are given here. Okay, suppose that we are interested in diagnosing cancer patient who visits a chest clinic. Let us A represent the event person has cancer, B represent the event that person is a smoker. This is completely probability. We know that the probability of the prior event, that is PA, is 0.1 on the basis of the past data. That is 10% of the patient entering the clinic turn out to have cancer. That is on the past data. We want to compute the probability of the posterior event, that is PA by B. It is difficult to find this out directly. However, we are likely to know PB by considering the percentage of the patients who smoke minus, suppose that is PB equal to 0.5. We are also likely to know PB by A by checking out our record. It is again from the past event. Record the proportion of the smokers among those diagnosed. That is PB by A is 0.8. So both the data, that is PA equal to 0.1 based on the past record, and PB by A equal to 0.8 is also based on the past records, and PB is 0.5, that is also based on past records. So now you can use the Bayes theorem and compute. Thus, in the light of evidence that the person is a smoker, we revise our prior probability from 0.1 to posterior probability of 0.16. That there is a significant increase, but it is still unlikely the person is having cancer. Okay, one more example. Suppose that we have 2 bags containing black and white balls. One bag contains 3 times as many the white balls as blacks. The other bag contains as many black balls as white. The other bag contains 3 times as many black balls as the white. Suppose we chose one of these bags at random. For this bag, we select 5 balls at random, replacing the each balls after it is been selected. The result is that we find 4 white balls and 1 black ball. So let us see what is the probability. So A be the random variable bag chosen, that is A1, A2, where A1 represents the bag with mostly white balls and A2 represent bags with mostly black balls. So the theorem applies here. And B be the event where 4 white balls and 1 black ball chosen from 5 selections. Then we have the calculation that is A, P, A1, B, and based on this base rule, we have this calculations. So at the here, instead of going to the complete probability, if you can just take the formula and you can get the solution. Okay, advantages: allows a principled approach to the exploitation of all the available data with an emphasis on continually update one's model as the data accumulates. Also, it is seen in the consideration of what is learned from the positive mammogram. In the Bayesian reasoning, as I told initially, based on the assumptions that 1% of the women aged 40 who participate in a routine screening have breast cancer, and 80% of the women with breast cancer will get positive tests. That is based on the assumptions. And 9.6 of the women without breast cancer will also get the positive test. Evidence: a woman in this age group had a positive test in the routine screening. So the problem: what is the probability that she has breast cancer? Okay. Again, assumptions: 10 out of 1,000 women aged 40 who participate in a routine screening have breast cancer. 800 out of 1,000 of women with breast cancer will get the positive test. And 95 of the 1,000 women without breast cancer will also get positive test. So the problem: if 1,000 women in this age group undergo a routine screening, about what fraction of women with the positive test will actually have the breast cancer? Okay. So again, the assumption: 100 out of 10,000 women aged 40 who participate in the routine screening have breast cancer, and 80 of every 100 women with breast cancer will get positive test, and 950 out of 9,900 women without breast cancer will also get positive test. And so here the problem: if 10,000 women in this age group undergo a routine screening, what fraction of the women with positive test will actually have the breast cancer? Okay. Before screening, we have 100 women with breast cancer and finally 9,900 women without breast cancer initially. After the screening, that is 80 women with breast cancer and positive test, 20 women with breast cancer and negative test, C is 950 women without breast cancer and positive test, and 8,950 women without breast cancer and negative test. So the proportion of the cancer patients with positive results within the group of all patients with positive results. So based on the formula. Okay. So here comes your conditional probability. Okay. Now the reasoning. Before screening, 100 women with breast cancer and 9,900 women without breast cancer. So in the last, as we seen, A is 80 women with breast cancer and positive test, B 20 women with breast cancer and negative test, breast cancer and positive test, and D 8,950 women without breast cancer and negative test. So the proportion of the cancer patient with positive result within the group of all the patients with positive results, that is A divided by A plus C, and you are getting 7.8%. Okay. The Bayesian reasoning, that is based on the prior probability. Okay. So you can see here the probability of C coming as 1%, probability almost C, that is 99%, you are getting 99 by 100. A is coming as 0.008, B 0.002, C is coming 0.095 and D 0.895. So rate of the cancer patient with positive results within the group of all patients with positive result, it is coming as A divided by A plus C is 7.8 percentage. So this is the formula we are applying. Okay. So common mistake to ignore the prior probability. Usually in the Bayes theorem it happens. The conditional probability slides the revised probability in its direction but doesn't replace the prior probability. A natural frequency presentation is one in which the information about prior probability is embedded in the conditional probabilities. The proportion of people using Bayesian reasoning rises to around half. Test sensitivity issue, or if it is like if two conditional probability are equal, the revised probability equals the probability. So the prior is the probability of the parameter represent what was thought before seeing the data. The likelihood of the probability of the data given the parameter and represents the data now available, and the posterior represent what is thought given both prior information and the data just seen. So posterior corresponds likelihood into prior. So why Bayes theorem? Because Bayes answers the question we really care about. Prediction. I have disease plus test positive versus prediction test with disease. And prediction A better than B versus with data versus prediction extreme data A equal to B. So Bayes is natural versus interpreting as C1 or a p-value. Okay, these are some of the examples again. So you are waiting on a subway platform for a train that is known to run on regular schedule. Only you don't know how much time is scheduled to pass between the train arrivals, nor how long it has been since the last train departed. So you are just waiting for the train, but you don't know the exact timing or when the last train has departed and what is the interval between each trains. As more time passes, do you grow more confident that the train will arrive soon, since its eventual arrival can only be getting closer, not further away? Or grow less confident that the train will arrive soon, since the longer you wait, the more likely it seems that either the scheduled arrival times are far apart, or else that you happen to arrive just after the last train left, or both. So if you are waiting and you don't know exactly the timing or when the last train departed or the train arrivals interval, so you'll get two types of thoughts in your mind. One is grow more confident that train will arrive soon, or grow less confident that train will arrive soon, but since the longer you wait, more likely it seems that either the scheduled arrival are far apart, means you are thinking that the arrival time between both the trains is very long, or you arrived at the nick of the time that the train just left. Okay, if you choose A, that is you are thinking like a frequentist, Or if you choose B, you are more thinking like a Bayesian. Okay, one more example. An opaque jar contains thousands of beads, but obviously a finite number. You know that all the beads are either red or white, but you have no idea at all what fraction of them are red. Means you just know that the colors are red or white, but you don't know exactly the numbers. So you begin to draw the beads out of the bin at a random without replacement. So you notice that of the first several beads have become red. As you observe more and more, the red beads is conditional probability, that is conditional upon the previous draws colors of the next bead being red. That is, it is either decreasing as it must, since you are removing the red beads in a finite population, or increasing because initially you didn't know that there will be so many reds, but now it seems that the jar must be mostly red. So you are having two conditions, since you do not know how many red beads or white are there. So either that the red color beads will be decreasing because it has a finite population, or it can be increasing if you feel because you don't know that there are more red beads inside the jar. So again, if you choose A, that you are thinking like a frequentist, or if you choose B, you are more thinking like a Bayesian. So limiting relative probability of A limiting times A happens in the n trials divided by n. A nice definition mathematically, but not so great in practice. So we often appeal to symmetry. What if you can't get all the way to infinity? Okay, these are so many other examples for the probability given. Okay. So Bayes' theorem is used to take a prior probability, update it with the data that is likelihood, and get posterior probability. Okay, this is one medical test example. So in a test that is 95% accurate when a disease is present and 97% accurate when the disease is absent. Suppose that 1% of the population has the disease. What is P? Have the disease or the test positive? So I'm getting probability of approximate 0.24. Okay. Okay, if Bayes is so great, why it is not popular? Actually, initially it was without this Markov chain Monte Carlo, and hence it was not made practical. But now it is actually used with this Markov chain Monte Carlo. You seeing in the quotes which I will be giving you. Some people distrust pair distribution, thinking that sign should be objective as if they were more probable. Base is becoming more like common due to this MCMC, that is Markov chain Monte Carlo. Initially, it was I told it was not very common, but now with the application of this MCMC, it has become quite common. So, what is this MCMC? Markov chain Monte Carlo sampling provides a class of algorithms for systemic random sampling from higher dimension probability distribution. Unlike Monte Carlo sampling methods that are able to draw independent samples from the distribution, Markov chain Monte Carlo methods draw samples where the next sample is dependent on the existing sample, called the Markov chain. This allows the algorithms to narrow in on the quantity that is being approximated from the distribution, even with a large number of random variables. So the name, as you can see, it combines two properties, that is Monte Carlo and the Markov chain. So Monte Carlo is the practice of estimating the properties of a distribution by examining the random samples from the distribution. Example, instead of finding the mean of the random distribution by directly calculating it from the distributions equation, a Monte Carlo approach would be to draw a large number of random samples from a normal population and calculate the sample mean of those. Okay, the benefit of this Monte Carlo approach is clear. That is, calculation of the mean of a large number of sample numbers can be much easier than calculating the mean directly from the normal distributions equation. Okay, this benefit is most pronounced when random samples are easy to draw and when the distributions equations are hard to work in other ways. The Markov chain property of this MCMC is the idea that the random samples are generated by spatial sequential process. Each random sample is used as a stepping stone to generate the next random sample, hence the chain. A special property of the chain is that while each new samples depend on the one before, new samples do not depend on any samples before the previous one, and this is the Markov property. Okay. But for the general cases, mathematics is not traceable here. However, the MCMC has given us a way around. We don't need to evaluate any integral. We just sample the distribution many times. Like example 50k, that is 50,000 times, 50k times, and estimate the posterior mean middle of 95% from that. Yeah, one moment, please. Okay. So how does this MCMC work? It is based on Metropolis algorithm. Okay. So these days we typically use Gibbs sampling, which is a variation on the Metropolis. Old softwares are like Bucks, Bayes using Gibbs sampling, and the newer function is JAX, just another Gibbs sampler. And the newest is Stan, uses Hamilton Monte Carlo. This is the multivariate distributions. Thresholding. Okay. Bayesian methods use probability models for quantifying uncertainty in inferences based on the statistical data. In Bayesian estimation, we start the formulation of a model that we hope is adequate to describe the situation of the interest. and observe the data, and when the information available changes, it is necessary to update the degrees of belief, that is probability, and evaluate the fit of the model. If necessary, we compute predictive distributions for the future observations. So prejudice or scientific judgment, it is where to check it. The selection of a pair is subjective and arbitrary, and it is reasonable to draw conclusions in the light of some reason. Okay. So let us do, everybody please open your heart. Solve some codes for this Bayes theorem. Okay. First, everybody, 1 minute. I will just share. Okay, I did not share the screen. Okay, set the working directory. You can see one package is this MCMC pack. Check it out in the Google package. Working, everybody, the codes? Yes or no? The codes are working, Chinmay, Divya.
No, sir, we have to download the package.
Okay, please do it. Gayatri, Geeta.
So installing packages.
Okay. Okay, please do it. So we've done for everybody the package installation. Yes or no? So the package installation is done. That is our R2 wins bugs and MCMC. Everybody. Okay, if it is done, let us do this. So you are setting the seat as to 123. Initial value you are taking n is 30, sigma 2 and mu 3 you are already assigning for yourself, and you are taking the normalization function you are giving. Next, you can do the mean of your y. Remember, in the Bayesian, you are doing the normalization and then you are taking the mean. Sai Divya, Sarvani, which step are you in? The value assignment is done. Sai Divya,
Yes, sir.
okay. Priyanka, okay.
Doing it, sir.
Okay. Prabhu, Chinmay,
Done, sir.
okay. So you need to pair the parameters of all the values which you used initially. Then specify the weight. Then take the posterior mean. And then the posterior standard deviation. Okay. So then you have to do the direct stimulation of the posterior normal. Okay, done. Did you all get this base one normal? Did you all come to this base one normal and you got the quantiles? Did you all do this quantile function? Okay, so we're setting the base theorem here. and you are taking the quantiles. So as you can see, 2.5 you are getting 25, 50 is coming here, 75 and 97.5. That is the quantiles in the 4 parts. And you are calling the base function, that is MC normally function you are calling. Finally, you are printing the summary. So you can see your iteration is 1 to 10,000. Thinning is 1 given, number of chains 1 taken, mean, standard deviation, time series, native Messi, a standard error, you can see here, and the quantiles. So you can plot the functions. So you're giving the plot function like x, and you are giving the values here, drawing the lines, and then in the top you are giving the legend, that is which is prior, likelihood, and posterior. So till so far you have not given any data. Without data you have done it. Now you are giving some data, that is n equal to some data you are giving now. So far you did not give, that is just with 0 and a minimum data you had done the word, done function. So now you are assigning the value, that is n. So initial data was for the patients. Now this data is for the number healed. So patient data was initial, that is the n. X is for the number healed. So check out the observed population now. Observed proportion. So call the objective function. Now you have to call the optim to search the root with initial values at 3,3. So optim it is 3.3, sorry 3,3. Then you are preventing, ignore the warnings. So now you are going for the direct simulation. Okay, so till this step everybody has done. Till base you're calling the base theory function for the direct simulation. Till this step you all have done. Yes or no?
Yes, sir.
Okay, then you can print the quantiles again for the data which you just now assigned. So you are assigning the parameters. You're calling the MC binomial beta function for 10,000 stimulation. Again, you are printing the summary for this base, the variable whichever you have taken. Now you can plot the beta density. Everybody is getting the plot. Chinmay, Divya.
Yes, sir.
Okay. Gayatri. Divya.
Doing it, sir.
Okay. Prabhu, Priyanka.
What, sir?
Yes, sir.
Okay, yeah. Okay, got the plot? Okay.
So Shravani, he lost a connection. She'll join back, sir.
Okay. So let us, you can add the simulation lines to the plot and you can give the legend. So lines you are drawing and the legend. So you need to import the last class data, the one which I had given for the homework. Same data set you have to load in R. Hopefully everybody can do this. Please load the previous data set which I had given as homework. All are able to load the data of the previous class? All could load the data of the last class, yes or no? This function is successful for all? Yes or no?
Yes, sir.
Okay. So you are using the data for your base theorem here. So that is the last class data initially you used for some other application. Here you are using for some other application. That is how you can use the data sets given. Okay, the plot is coming. I think I given the codes to all. Yes. What happened? The plot did not come. Yes. So everybody got this plot?
Doing, sir.
Okay.
Done, sir.
Okay, everybody has done? Chinmay?
Yes, sir.
Okay. Priyanka? Divya?
Got it, sir?
Okay. Okay, so this ends your R classes, everything. So tomorrow I need to take for you transcriptomics. So Chinmay or Divya, can you help me out with the transcriptomics, the codes? I think both of you had attended the transcriptomics workshop. Chinmay? Chinmay, are you there?
Yes, sir.
Yeah. The theory part I will be taking. Can you go ahead with the using the Galaxy?
I have to look on, sir. It's been, I mean, I haven't practiced again.
Okay.
I have to look.
Divya? Divya? Can you go ahead with the Galaxy tomorrow? Divya, I'm not able to hear you. Yes or no? Divya, can you do it? Okay, no problem. Okay. So what I will do, anyway, tomorrow I will be taking the theory for the transcriptomics, and if tomorrow time permits or Sunday, I will be taking the course for your this one transcriptomics in Galaxy. Okay. So I need to even discuss regarding the projects. Tomorrow before starting the class, whoever are joined here or whoever will be joining tomorrow, if you all are coming we can discuss the projects before starting with the transcriptomics. Is it okay? You can also think a topic in your mind. I will discuss the topics and I will give some groups, maybe 3 persons in a group, and then you can start with the topics. If you want to go ahead with the publication, make sure that you are contacting the original data owner. Okay, I will give you one website wherein you can go through the several this one projects ideas you will be getting. And in the meantime, tomorrow I will not give any homework today. Actually. And one more thing I want tomorrow. Let me see. I will giving one short test just for 5-10 minutes. Then I will discuss the projects and then go with the transcriptomics class. So everybody, please try to retrieve few research papers in the areas of R using machine learning, and come back. So download few papers, but it should be all dealing with R and not with any other software. Okay. Then it will be easy for you for us to go ahead, and then you can see from where they have taken the data. Even if it is GitHub, in the GitHub all the data may not be all free. Still, it is always good to contact the owner before going ahead with the publications. So most of the data, whatever you will be using, it will be from the this one GitHub. So think it out in your mind. If whoever will be coming tomorrow, I hope to complete the anyway R is complete, so I have to just take the transcriptomics. Hopefully tomorrow and day after tomorrow I will complete it, and by Sunday your this course will get over. Those who wish to continue the projects, please let me know separately, so that I can give a separate time for the projects. Not in this weekends, maybe in the weekdays around 8 o'clock, but only for the people who are very much interested in the projects. Okay. So I will be ending it today here. So see you tomorrow. Tomorrow I will take little early, maybe by 7 o'clock tomorrow I will be starting the class. Okay. So initial 10-15 minutes I will give a short test, and then I will move on with the this one, introduction to transcriptomics. Okay then, good night everybody. See you.
Thank you, sir. Good night, sir.
Thank you, sir.
Yeah, thank you. Yeah, good night.
Thank you, sir.
Yeah, thank you. Good night.